Okay. Am I audible at the back? Is this working? Okay. Is it okay now? All right, very good. Thank you. All right, so we're going to talk about the love of physics and math. And so this is the most colorful front page of my presentation that I've ever used, because this is the first talk that I've given which talked about love. All right, so let's begin with the flower. Right, so we're going to talk about love. Everybody recognizes painting over here? No? Well, this is one of the great sunflowers, right? Well, paintings are beautiful, of course. And you can see over here some very lovely roses as well. These, by the way, are world-famous paintings. I'm not going to give out the names of the painters to you guys. I want you to go back and look those up. So there's many reasons for picking out these two paintings. Well, when we think of love, when we think of things that are beautiful, flowers come to mind. And when we think of the ways to express our love, art comes to the forefront, right? Hello, is it? I think it's somehow being switched off. Yeah, it's. Are we out of battery or what? Yeah, it's showing low battery, I think. Anyway, can you guys hear me at the back? Okay, good. So I'm just going to continue without that. Right. So let's now talk about so why do these paintings belong in a talk about the love of physics and math? Well, to begin with, you guys can see this couple of equations up there. These equations, these set of equations describe what is known as the Fibonacci series, the Fibonacci sequence. And the reason for picking sunflowers and roses, apart from them being very beautiful, is that there are patterns in sunflowers and roses. In particular, the way their florets and petals are arranged, which follow the Fibonacci sequence. Of course, in your math classes, you'll learn what difference equations are and how to solve them. But it's so beautiful to see that what is beautiful to the eye, what is pleasing to the eye, usually has some kind of a mathematical pattern behind it. And it's that love for physics and math, that love for math that we would like for you to experience while you're going to be here with us. So just to let you guys know further, the Fibonacci sequence came out when a mathematician sat down, well, Fibonacci himself, of course, he sat down and he thought, let's count rabbits. That's a fun story, and the way he thought about it, that's what led to the Fibonacci sequence. So there are patterns in nature, and when we try to describe those patterns mathematically, I would argue that the picture is even more beautiful. So let's continue with the flower. So far, I've taken you out of art, and I've taken you to math, and I've taken you to designs and patterns. Let's continue. When you're going to become a physicist, you'll see even richer patterns, right? The flowers that you see have colors, and it's the colors of the flowers that's the first and most attractive thing about the flowers. Now, where are those colors actually coming from? Well, those colors, well, eventually are coming from transitions that the electrons are making within the flower. And what describes those transitions. Of course, the lovely equation given by our good friend Schrodinger. And I'm sure you guys have heard somewhat about things being dead and alive at the same time, in particular Schrodinger's cats. So Schrodinger is the guy who gave us this beautiful, well, he gave us this very graphical way of looking at quantum physics, played a huge role in developing the theory. And it is, so when you're looking at a flower as a physicist, you're not just looking at the lovely colors, you're not just smelling the sweetness of it, you're also understanding कि वो रंग कहाँ से आ रहे हैं, what is causing that lovely beauty, and it's all there neatly described in mathematical equations. And of course, all right, so this was kind of interesting. So, I was just looking at when, it's a time for memes. So normal Shakespeare says to be or not to be, and the quantum Shakespeare version, of course, is going to be to be and not to be. And I'm sure when you're going to take the course on modern physics in your second semester, you'll get to appreciate a whole lot about it. Moving on, we have all kinds of floral patterns, right? So one of the biggest breakthroughs of the past 20 years has been our ability to actually make nanostructures, right? Of course, well, these are self-assemblies. These are examples of self-assemblies. But now we're at a level where we can actually sit down and we can move atoms and molecules from one point to another, and we can make structures out of those. The technique is called scanning tunneling microscopy, and these are STM images. So these STM images are, again, give you a visual representation of the electron clouds that are out there. What is making those structures? Of course, it's not just little things. Beauty is everywhere. And physics, the whole job of physics is to be able to describe all of that beauty, all the way from the very small to the very large. So what you can see over here is, well, this is not a real image. This is not a real image taken from a telescope, but this is really an artist's reimagination of it. But what's being shown is a solar flare, right? Now, where does this fit in? Well, this fits in to our understanding of, let's go back to colors and atomic transitions. So the same physics that tells us why certain things have certain colors, when you apply the same physics to the stars that you see around you, you know that the entire universe is made up of the same kind of matter, right? So basically, so of course, I mean, you can ask this question, as students of science, we all know that there's a whole lot of hydrogen and helium out there in the universe. And whereas there is, so one could naturally ask the question, how do we know that? Well, the reason that we know that is because hydrogen and helium, and for that matter, every atom has a characteristic light spectrum. There's certain characteristic colors that they give out. So when we go out there, when we look at stuff through our telescopes, we see those exact colors, and then we know that, okay, so everything is just made up of hydrogen and helium. So it's the same elements that we see out there in the universe. But that's not all. When we look at those spectra, we see that the spectra are somewhat shifted. So, we all know that colors are related to frequency or wavelength. And we also know about the Doppler effect. And we know that when something is moving with respect to us, there's going to be a Doppler shift in frequencies. When we look at those stars out there, when we look at those galaxies out there, we know exactly how fast those things are moving, precisely because the pattern of frequency shifts is consistent with the Doppler shift, right? So just by looking at simple mathematical equations and applying them to the universe, we understand a whole lot about our universe. Of course, that's not all. You can keep on going and going and going. And so right now we're living in a very exciting time because we've discovered one of the consequences of Einstein's theory of gravity. So there's certain things that mathematical equations and the beauty of mathematical equations can predict. And it might take 100 years to actually see them. For instance, Einstein gave his equations of gravity way back in 1916. Only in the past 5 years or so have we actually seen evidence of gravitational waves, direct physical evidence. So this again is an artist's recreation of what a gravitational wave is, but what's being shown is two black holes merging. So black holes again were predicted way back about 90 years or so ago. And gravitational waves were predicted a whole lot, about 100 years ago. We've discovered those, and then we've imaged also black holes. All right, so I don't want to take too much time. I'm just going to say that really, I'm just going to build on what Professor Sabi was saying earlier on, that this is always a joint effort. Physics experiments are huge. Not all of them, but many physics experiments are huge. They're costly, and they are human resource intensive and spread, and they require all kinds of expertise. So a big example is, of course, the Large Hadron Collider. So if I just talk about the Large Hadron Collider, you see over here, this little ring over here, that's 27 miles in circumference. So that's the scale of this experiment. A future circular collider is planned as well, which you can see is so much larger. Again, just to see a sense of scale, you see this gentleman standing over here, and you can see this huge detector. And all this was built, of course, designed by physicists, built by physicists and engineers, put together, joint effort and all. And so many more. You can just, the list goes on and on and on. You can talk about this huge experiment called the Ice Cube, which is being conducted currently on the South Pole, at the South Pole. For a size comparison, you can see the Eiffel Tower right here. So this is like small, minuscule compared to the scale of this experiment. And then we have this huge experiment which is planned called LISA. Laser interferometers going out there in space, circling, orbiting in space, and trying to detect gravitational waves, hopefully taking us to times before we can imagine right now. All of this, hopefully, you will experience over the next 4 years or so, and later on in life, maybe you can contribute to one of these great endeavors or design one of your own. I'm going to stop here. Thank you.